Paper 2 from May 22, Timezone 2. Starting off with balancing equation, where we have lithium to become lithium hydroxide by dissolving in water. Simple balancing equation. We're going to start off with 2 lithium hydroxide to make sure that we've got 2 water. We can have 2 water on the reactant side, meaning that we will need to supply 2 lithium and we'll end up with 1 hydrogen. We're given the mass of lithium as 0.2 grams. We need to find the molar concentration of lithium hydroxide. For that, we need to find what? The amount of lithium hydroxide in mole, and then divide that by the volume of water given. To find the amount of lithium hydroxide, we have to find the amount of lithium. Why? Because the molar ratio of lithium and lithium hydroxide is 2 to 2. 2 to 2, 1 to 1. Amount of lithium is going to equal to the mass of lithium as given by 0.2 grams over the RAM of lithium. What's the RAM of lithium? Look up on your periodic table and it will be given as 6.94 grams per mole. Let's do the math and we'll be given 0.0288 mole. Amount of lithium we have is 0.0288 as well as the amount of lithium hydroxide. Now, this much lithium hydroxide is in how much water? 0.5 dm cube. And this will give us the concentration as 0.0576 mole per dm cube. Our answer. We're then going to calculate the volume of hydrogen produced at specific temperature, pressure. What are we talking about? We're talking about usage of ideal gas equation, PV equals nRT. For that, we will need to work out the mole of hydrogen produced because the rest of the data we already know. What's the amount of hydrogen produced? Well, we're going to go back to the balanced equation. We have inputted 0.0288 mole of lithium and we will output half that amount because 2 to 1 molar ratio of lithium to hydrogen. 0.0144 is the amount of hydrogen that we know of. So let's put the values into the rearranged ideal gas equation. We're trying to find the volume. So volume equals nRT over P, which would equal to 0.0144 mole times R, gas constant. Look up on your data booklet, 8.31 joules per Kelvin per mole is the answer, times temperature. We are given 22.5 degrees Celsius. Do you put that value in? No, you don't. You have to convert that value to Kelvin, which would then be 273 plus 22.5, which would be 295.5 over pressure. Pressure we're given as 103 kilopascals. But let's convert that into Pascal. So we are given 103,000 Pascal. Now, this should give us the volume in the unit of meter cube. Why? Because that's the standard unit for volume utilized in PV equals nRT, provided we have used Pascal for pressure, not kilopascal. Do the math, and we'll be given 0.00343 meter cube. We can convert that into what value? cm cube. We are asked to put the value in cm cube unit, which would convert to 0.343 dm cube, and then 343 cm cube. Hydrogen gas volume collected, we theoretically postulated that to be 343 cm cube, but in reality, the actual volume produced was less than that. I can think of two reasons for that. First, we have used impure lithium sample. What does that mean? That means that the actual amount of lithium used that has reacted was not 0.0288, was not this value, but instead lower. And that would also affect the amount of hydrogen produced to be less than 0.0144 mole. I can think of another reason as loss of product. Maybe we have not successfully captured the hydrogen produced. Could be an answer. Maybe hydrogen gas has been used in combustion. Hydrogen can combust because we've got energy released from the reaction of lithium and water. It's an exothermic process. Energy released with ample amount of oxygen around hydrogen could lead to hydrogen combustion. So hydrogen volume used up. We have change in oxidation state of lithium, don't we? We go from 0 to +1 oxidation state. What that means is lithium has been oxidized by an oxidizing agent, and that oxidizing agent is going to be water. Why? Because water is in turn reduced by the reducing agent lithium. Water is reduced to H+. Water has been reduced to H+, where hydrogen of water has gained. Specifically speaking, it's the H+ of water has gained electrons to become reduced to hydrogen gas. I have previously mentioned that lithium with water reaction is exothermic. Well, the simplest physical observation we can make out is measure the temperature increase. Temperature rise can be measured by thermometer usage. What else can we think of? Well, think of the lithium, the lump of lithium floating on water surface. Maybe that lump may catch fire because there's heat being produced. Lithium lump catches fire. What other potential physical observations could we make? You could go with what I've just mentioned about hydrogen combusting, and that will create the pop sound. The pop sound that arises from that is hydrogen, the product, combusting. Pop sound from hydrogen combustion. Calcium having a higher ionization energy than potassium means that the electrostatic attraction between the nucleus of calcium and the valence electron, the electron being ionized, is stronger. And what are the reasons for that? It's because the nuclear charge, the effective nuclear charge of calcium is greater than potassium. There are more protons in calcium, isn't there? So the first point we're going to make is that the nuclear charge of calcium is greater. What other reasons could there be behind electrostatic attraction between nucleus and valence electron being greater? What if the distance between the nucleus and the valence electron is shorter? And that is actually true because calcium is smaller than potassium. Smaller atomic radius. Remember, how does the atomic radius change across the period? Decreases across the period. And this is why across the period, the ionization energy has a general trend of increasing. We have the energy levels of a hydrogen atom with the discrete levels converging towards high frequency, high energy, where n equals infinity represents the highest possible energy level. Two limitations to this model of electron energy levels is that, well, we know there are now sublevels, orbitals, that represent the position of electrons, and that's the more accurate version of atomic substructure. Therefore, we're going to say firstly that the model does not represent atomic orbitals that we would expect. Second, this model only applies to hydrogen with one electron, atom with only one electron. Only applies to atoms with one electron, and that's hydrogen. Electron transition for the ionization of hydrogen atom in the ground state would be an arrow starting from n equals 1, the ground state, all the way to n equals infinity. That would represent ionization energy. Electron transition in the visible spectrum means we have relaxation of an excited electron from n equals 3 or higher to n equals 2. And we are talking about the lowest electron transition. I'm going to color this in a different color. Any of the following relaxations could correspond to visible wavelength. However, we are interested in the lowest energy, which would be the red color. The highest energy visible wavelength would be violet, and that probably would be n equals 6 to n equals 2. So what we're interested in is n equals 3 to n equals 2. That would have the lowest energy gap corresponding to the red wavelength of the visible spectrum. Cell potential calculation question, where we have iron 2+ being further oxidized to Fe3+, and we'll represent this oxidation half equation as Fe2+ turning into Fe3+, releasing one electron. This will have an electrode potential value that is negative. We're going to introduce negative sign. Why? Because this is oxidation, not reduction. And the value we will be using is right here, plus 0.77, plus 0.77, which means it would actually be minus 0.77. Who's going to be in the reduction half equation? It would be the bromine. Bromine is going to be reduced, Br2, gaining 2 electrons to become 2 Br minuses, would have electrode potential, reduction potential of what value? We would expect that to have a more positive electric potential for actually a spontaneous redox reaction to occur, plus 1.09, meaning that the cell potential E theta would be the 1.09 minus 1.09 minus 0.77 volts, so that we end up with 0.32 volts. Remember, why am I subtracting 0.77 from 1.09? Because we're going to minus the electric potential at the anode from the electric potential at the cathode. E theta cathode minus E theta anode. And at the cathode, we have reduction occurring. And where's the reduction? Bromine reduction. What's happening at the anode? Oxidation, and iron 2+ is being oxidized. Iodine is the halogen below bromine. And like bromine, will it be able to oxidize iron? It can if the electric potential value for iodine is going to be more positive than iron. But does it? Where is iron electric potential? We have just located iodine electric potential to be plus 0.54, which is less positive than iron electric potential. Meaning what? Meaning that iodine cannot oxidize iron. No, because iodine has less positive electrode potential than iron 2+. Electrolytic cell of molten zinc chloride at 450 degrees Celsius. Why so high temperature? Well, we do need to melt our electrolyte, zinc chloride. And zinc chloride is what? An ionic compound. And ionic compounds in general require high temperature for melting. 450, we have molten zinc 2+ and Cl- ions that will be migrating to cathode and anode respectively. Cathode will be attracting our zinc 2+ ions. Zinc 2+ liquid will be gaining electrons, specifically 2 electrons, to become zinc liquid? That one I'm not so sure. Why? Because zinc will have quite a high melting point, being a metal, and due to the nature of metallic bonding, zinc is likely to be a solid if the melting point is higher than 450. We do need to check that, and let's check that by going to melting points and boiling points of the elements. I do see zinc to have 419.5 degrees Celsius melting point, which is lower than our electrolytic cell temperature. Therefore, it will be molten and therefore liquid state. We don't need to be concerned about chlorine because chlorine will be oxidized. Chloride ion will be oxidized into chlorine gas without any doubt. Using the two reduction oxidation half equations we have just derived, we can formulate the full redox reaction, the full redox equation by simultaneously adding the two half equations. Now let's add the two to derive zinc 2+, 2Cl-, but together they will actually ionically attract each other to become zinc chloride liquid. So let's represent zinc chloride to zinc Cl2 liquid, turning into zinc liquid and Cl2 gas. That's the equation that represents our electrolysis. Now, we were given the guidance of using section 7 of the data booklet. We have just used that in our previous answer, just to make sure that the zinc produced would be in liquid state. Hydrogen reacts with iodine to produce hydrogen iodide, and we have several experiments with initial rates. What are we doing? We are going to be comparing the concentration values with the initial rates to find the order with respect to each reactant. That's what we're going to do. Starting off with hydrogen, let's compare experiment 1 and 2. Why? The initial concentration of iodine remains the same, so that we can compare how tripling the H2 concentration will also triple the initial rate to indicate that, to infer that we have first order relationship with respect to hydrogen. And we also would need to do the same work for iodine by comparing 2 and 3 experiments. With H2 concentration remaining the same, we are doubling the iodine concentration, and at the same time, we notice how the rate doubles. That tells us that we have first order relationship with respect to iodine as well, telling us that we can write the rate expression as rate equals K H2 and I2. From the rate expression, we can apply some values either from experiment 1, 2, or 3, the values of concentrations H2, iodine, as well as the initial rate, to work out the K value. Let's try using experiment 1. So, rate, we are going to use 1.2 10 to minus 6. The unit for rate is going to be mole per dm cube per second, equals to K times 2 times 10 to minus 3, 3 times 10 to minus 3. Now, that is going to equal to 6 times 10 to minus 6. And the unit is going to be mole dm minus cube squared, so mole squared per dm to the power of 6 minus 6. Now let's flip the concentration values to the left side so that we can do the following division. Nice values so that we can easily do the calculation, probably without using the calculator. Let's attempt that. So we will have multiplied 10 to minus 6 cancelled out. Goodbye. Which leaves us with 1.2 over 6. That can be simplified as 1 over 5 or 0.2. Mole to the power of minus 1 dm cube s to the power of minus 1 is K, is the rate constant. Reactant molecules must collide successfully for there to be a reaction. There may not be a reaction if the two colliding molecules do not successfully collide and actually bounce off. So we want to make sure that the colliding molecules will have, colliding particles will have energy that is greater than the activation energy of the reaction, EA. And at the same time, the reacting particles would be colliding at the correct with the correct orientation, at the correct geometry. Correct colliding geometry. Equilibrium expression Kc for our reaction would be product concentration over reactant concentration, therefore Hi. Let's not forget the coefficient of the product 2, therefore Hi squared, concentration of Hi squared, over H2 and iodine I2. We have been told that this reaction, the forward reaction, is endothermic with a specific delta H value. And we are given some entropy values of the reactants and product and asked to calculate delta S. Delta S is easily calculated by taking away the reactant entropy value from the product, which means the arithmetics we have to do would be 206.6 times 2. Why times 2? Well, remember, there are 2 moles of product for every 1 mole of reactants inputted. And therefore, we have to acknowledge this coefficient stoichiometry. Therefore, we'll be multiplying the product entropy value by 2 and then take away the reactant entropy values. Do the math and we'll be given 166.5 joules per Kelvin per mole. Now that we have delta S value, the next question is probably going to ask us to use delta H and delta S values to work out delta G. But before then, we are asked how delta S value would change if iodine used was, instead of solid, gas. Let's look at how our calculated delta S value is positive, which completely makes sense because we are producing 2 moles of gas from 1 mole of gas and 1 mole of solid. Yes, gas is more chaotic. There's more disorder to gas than solid. Therefore, there's an increase in the disorder of the system. Positive entropy change value. Positive entropy change value does make sense. But what if we swap what if we introduce gaseous iodine so that in both reactant and products, we start off with 2 moles of gas and end up with 2 moles of gas? There isn't going to be as much increase in the disorder. Therefore, entropy value will get less positive. It might actually become near 0, but we don't know for sure. But what we can say for sure is that delta S value decreases or becomes less positive. Why? Because gaseous iodine has greater disorder than solid iodine. We could even say that because 2 moles of reactant gas end up as 2 moles of product gas. There we go. The delta G calculation question that I have predicted. what is the equation that we need to use for delta H, delta S usage? Delta H minus T delta S equals to delta G. We already know the values for delta H to be plus 53, was it? I believe the value was 53. Let's remember, kilojoules per mole is the standard unit for delta H, which is not the case for delta S. So we're going to have to make sure that the delta S value we quote will be turned into kilojoules per Kelvin per mole. Instead of using 166.5, we will use 0.1665 kilojoules per mole per Kelvin. Then we will also quote the temperature at which our reaction system is taking place, 298 Kelvin. It will give us kilojoules per mole value. Do the math and we will be given a delta G value of 3.4 kilojoules per mole. Quite a small one. And also positive, and that's disappointing. That means that our reaction is going to be non-spontaneous. A positive delta G value means that the reaction is non-spontaneous. Nicely linked to KC calculation question type. Delta G can also be linked to Kc value. How? Remember, delta G equals minus RT ln K. We know the R value, the gas constant. T value, we are again asked to utilize 298 Kelvin, room temperature. So, delta G value we have calculated to be 3.4 kilojoules per mole, but we're not going to use that value. You're not going to use that value either because you want to make sure that we use the same unit that will cancel out with the gas constant unit. What's the unit for gas constant? 8.31 joules per Kelvin per mole. We have to make sure that the delta G value we quote is in joules per mole. Therefore, not 3.4, but 3,400 joules per mole is our delta G value. Times ln K. We're going to have, before I times the ln K, I'll have to times 298 Kelvin first, then ln K. Kelvin units will nicely cancel out with itself. Mole, joules, puts us in a nice position to work out K value as ln K will equal to 3,400 over minus 8.31 times 298 Kelvin. K will be the exponential of that, and if we put the values into calculator, Kc is going to be 0.25. Iron sulfide must be pretty shiny for it to be mistaken for gold. Iron 2 plus is ionically bonded to S minus 1, 2 sulfurs. The electronic configuration of Fe2 plus, but firstly, what's the electronic configuration of iron? Well, remember in D block, we have the sequence of scandium, titanium, vanadium, chromium, manganese, iron. That's where the iron is, the 6th 3D element. Then it's going to be cobalt, nickel, copper, zinc. We're interested in the iron. Now, the condensed electronic configuration of iron is what? Ar, 4s2, 3d6. But if we have ionized form of iron, 2 plus, 2 electrons removed, we will want to make sure we remove 2 electrons from the 4s not 3D. Why? Because yes, empty 4s orbital is at lower energy than 3D, so that we fill in 4s first according to the Aufbau principle. But when we are removing electrons, the occupied 4s orbital is at higher energy than 3D. And therefore, the ion 2 plus is going to be Ar3d6. But you're not going to write Ar3d6 because the question has asked us for full electronic configuration. So if you were going to write argon, condensed electronic configuration, read the question carefully. We are going to start off with all the way from 1s2, 2s2, 2p6, 3s2, 3p6, now to 4s, instead of 4s2, 3d6. Okay, so there's going to be an increase from the 8th to 9th ionization energy. That's an awfully high successive ionization energy. But why are we dealing with 8 to 9? Look at the electronic configuration. How many electrons are there in the ion atomic state of ion? Eight. We've got 2 in 4s and 6 in 3D. Now we count 3D to be in the 4th energy level, don't we? So overall there are 8 electrons in the 4th energy level, which means when we are trying to remove the 9th electron, the 9th electron will be from the 3p orbital. 9th electron is from the 3rd principal energy level, which is a lot closer to the nucleus, which is at lower energy, which is for which reason the electrons in the lower energy are more tightly held by the nucleus, more difficult to remove. Large increase due to 9th ionization energy taking place at 3rd main energy level. Compared to 8th ionization energies, 4th energy level. 3rd energy level, you have to state the statement. 3rd energy level is closer to nucleus and at lower energy state than 4th energy level. Therefore, more energy required for ionization. Oxidation state of sulfur, too easy. We've already seen that right at the beginning, 2b minus 1. Bonding in iron is metallic, but we're not going to get 1 mark for stating metallic. We actually have to elaborate what metallic bond is made up of. It's made up of electrostatic attraction. Bonding is always about plus and minus attractive force. Electrostatic attraction between lattice regularly stacked metal cations, in our case iron 2 plus cations, and what else? Delocalized electrons. Specifically, 2 electrons would be delocalized per every Fe atom. Catalysts provide an alternate reaction pathway with a lower activation energy, and in doing so, the rate of reaction is increased. That's how we're going to answer the question. Provides alternate reaction pathway. And this alternate reaction pathway has lower activation energy, thereby decreases reaction rate. We're not going to mention this in this question, but for equilibrium, for reversible reaction, catalyst. Oh, did I just say decrease reaction rate? That's so stupid. It's increases. Apologies. Increases. Reversible reaction, there's the forward and backward reaction occurring simultaneously. Catalyst affects both reactions. Maxwell-Boltzmann distribution curve. X-axis is kinetic energy. Kinetic energy. Y-axis is going to be number of particles. Number of particles. The standard distribution curve that we draw is going to have this shape. Maybe I've drawn the finish line to be too high. I'm going to reduce that down slightly. Now let's label this as T1. We are going to draw T2, where T2 is at higher temperature. I'm going to make sure that both T1 and T2 starts at the origin. The lower temperature T1 will peak at lower kinetic energy, but the higher temperature T2 will finish higher than T2, like that. So I'm not very happy with this diagram. I'm going to make sure that we're near 0 for both T1 and T2. Okay. Hopefully what you draw is a smoother curve than mine. Temperature increase will be counteracted by the system favoring the backward endothermic, the endothermic backward reaction. That means the position of equilibrium, POE, shifts to the reactant side, meaning the percentage yield of SO3 product decreases. Temp increase counteracted by system, equilibrium system favoring. Here's the key term, endothermic backward reaction. Yes, to be able to answer questions like these, we have to be given the information of the forward reaction enthalpy change value. We don't need the specific value, but we need to know if it's positive or negative. Endothermic backward reaction. As a result, the position of equilibrium shifts to the reactant side. If you don't write what I'm about to say now, you're only going to get 1 mark, because after all, we have to state the effect that SO3 percentage yield decreases. SO3 can easily be drawn to have 3 double bonded oxygen. And why is that? Sulfur may go beyond the octet rule to have expanded octet, where it has 6 valence electrons. We will have 3 electron domains, with each electron domain containing lone pairs, 3 lone pairs, forming double bonds with oxygens, 2 electrons each. The electron domain geometry of SO3 is trigonoplanar. Trigonoplanar with 120 degrees between the electron domains, and that's the bond angle to allow bonding pairs to be located as far apart from each other as possible. Well, let's add water to SO3 to form H2SO4, sulfuric acid, easy. A bit of illusion, a bit of digression to acids and bases topic. Factories produce sulfur dioxides. Sulfur dioxides combine with oxygen to become sulfur trioxide, and sulfur trioxide in the atmosphere will dissolve in water vapors, leading to acid deposition. Sulfuric acid falling down. Meaning of strong Bronsted-Lowry acid is proton donor. That completely dissociates, like HCl. Like sulfuric acid, like nitric acid. In this question, we learn about how hydrogen cyanide can be formed from methane, ammonia, and oxygen. We don't need to understand exactly what the mechanism behind this formation is, but what we can tell here is that ammonia is going to act as a Lewis base for its ability to donate a lone pair. Donate a lone pair. Again, we don't need to know how the donated lone pair will trigger any mechanism at all beyond IB. But we can be assigned the specific pH value of ammonia, pKb value, so that we can work out the pH. How? What's the calculation method for pH of base acids? Write the Kb or Ka, in our case Kb expression first. Kb expression derived from where? NH3 acting as a base, as a weak base, by reacting with water and then turning into a conjugate acid to produce OH minus. OH minus is the important species produced because that determines P or H. With this basic activity in the indicating equation of ammonia written out, we can write the Kb expression as what? Kb equaling to NH4 plus conjugate acid concentration multiplied by the OH minus concentration divided by the ammonia concentration. We're going to skip the water concentration in our Kb expression, and we are told that Kb is what? 10⁻² minus 4.75. How do I know immediately how pKb converts to Kb? Well, remember, pH can be converted into H plus concentration by being times to the power of. The concentration of ammonia is given as 1 times 10 to minus 2. 1 times 10 to minus 2. Well, we know that the exact equilibrium concentration of ammonia is not going to be that, slightly lower, but the OH minus concentration is going to be very small, negligible, so that we can approximate the equilibrium ammonia concentration to be equal to the initial ammonia concentration. Remember that. OH minus concentration is what we're trying to look for, but we know OH minus concentration equals to the ammonium ion concentration as well. Why? Because those two products are produced in 1:1 molar ratio. So we can represent OH minus squared over 1 times 10 to 2 to be our Kb. Let's do the math to work out OH minus. If we do the math, OH minus is going to be calculated as 4.22 times 10 to minus 4. Let's not forget the unit, big M. With this, we can find the POH. How? POH is going to equal to minus log OH minus concentration, which in turn will give us the value of 3.37. If we know POH value, we can work out the pH value. From where? From the ionic constant of water equation. Ionic constant of water equation is what is H plus concentration times OH minus concentration times, H plus multiplied by OH minus concentration equals to 10 to minus 14, which can be minus logged to become pH plus POH equals 14. Therefore, our answer would be pH equaling to 14 minus 3.37, answer being 10.63. Sounds about right for the pH of a weak base. Will ammonia form a buffer solution when it's mixed with HCl? Yes, it will, provided that ammonia amount is in excess. Because after all, we want there to be excess amount of ammonia and excess amount of its conjugate acid, ammonium ion, ideally in 1:1 molar ratio, because that's what buffer systems are. But unfortunately, in our reaction mixture, we have more HCl. HCl is in excess, not ammonia. Therefore, when the weak base reacts with strong acid, yes, we will produce ammonium ion, but we will completely neutralize all of the ammonia that we started off with, so that we don't actually end up with any ammonia, with any weak base to counteract H plus addition. No, because all ammonia neutralized by HCl, meaning that no weak base is left to counteract, to neutralize H plus addition. Ideally, we want excess 1:1 ratio of, let's put excess behind ratio of 1:1 ratio of excess NH3 and NH4, the conjugate acid. Needed. We need this mixture for buffer effect. Sigma bond is the axial overlap of an s orbital and another s orbital. We can illustrate this as follow, where the overlap can be shaded. Not only is sigma the axial overlap of s orbitals only, but an s orbital with a p orbital. Again, there would be an overlap. The overlap shaded as follow. And there's one more combination. And what combination do you think that is? It would be between two p orbitals. But take caution here. The p orbitals overlapping must be axial, must be head to head. cannot be sideways because sideways overlap of p orbitals is what we define as pi bond. Sideways overlap of parallel p orbitals is a pi bond. We're back to hydrogen cyanide. If we draw hydrogen cyanide, what do we make out? We make out a nitrile carbon triple bonded to nitrogen and carbon single bonded to hydrogen, where there would be 2 sigma bonds, that's CH and CN, and 2 pi bonds. Carbon will be sp hybridized. Why? Because there need to be 2 p orbitals that will parallelly overlap with 2 p orbitals of nitrogen. If I draw this out, we will have a vertical, let's call this py of carbon with py of nitrogen. That forms first pi bond, while the second pi bond will be formed by, look at this artistic drawing of pz orbital, where the latter half of our hourglass p orbital is going into the plane, the frontal half of the hourglass p orbital is coming out of the plane. Now let's represent that as pz of carbon, and another pz of nitrogen can be drawn as follow. And where are the 2 pi bonds? The 2 pi bonds arise from the overlap of 2 py's. The second pi bond arising from the overlap of the 2 pz orbitals. Now, apparently hydrogen chloride has lower boiling point, has quite a low boiling point, and hydrogen cyanide has a high boiling point, high enough for it to be liquid at room temperature. Hydrogen chloride actually is difficult to be liquid at room temperature, but gas, which means that we always have to have HCl dissolved in water to actually deal with aqueous HCl solution. Why is that the case? The molecular mass are similar. In fact, HCl bigger, which means that HCl has greater London dispersion forces. None of them have hydrogen bonding, which means that dipole-dipole forces for HCN must be significantly stronger than HCl, or dipole-dipole for HCl significantly weak. HCN has stronger dipole-dipole. Why would HCN have stronger dipole-dipole? It's going to be to do with the polarity of the intramolecular bonds, CH, CN. We would expect there to be polarity between carbon and nitrogen, where nitrogen is more negatively polar. And the same would be seen in HCl. Again, chlorine will be more electronegative and therefore partially negative, while hydrogen is partially positive. It seems that if we compare the electronegativity differences, the electronegativity value differences, the CN electronegativity value difference should be higher than HCl, but let's not go this far. It's beyond IB. Cyanide is a ligand. Why? Because cyanide has a lone pair, not on the nitrogen, but on the carbon. Therefore, it can act as a ligand by donating its lone pair and basically dative covalent bond to transition metal ions. And when it does, it causes d orbital splitting. Ligand binding causes d orbital splitting. That's the start of transition metal complex ion coloring. The d orbital is split to lower and higher d orbitals. 2 sets of d orbitals. Out of 5 d orbitals, there will be a set with lower and another set with higher. Energy would be absorbed. I'm going to use a different color. Energy absorbed to promote an electron from the lower to higher d orbital. What's next? The energy gap in the 2d orbitals, the 2d orbital levels correspond to light in the visible wavelength. And it's the complementary color that we see. Complementary color of that visible wavelength absorbed is observed by our eyes. That's how we observe transition metal complex ions to be colored. Allotropes of carbons include what? Diamond, graphite, and Buckminster fluorine, C60. We're going to look at C60 and diamond, especially their comparison and contrast. Differences between the bonding of carbon atoms in C60 and diamond. Okay, we would be acknowledging how in C60 each carbon is bonded to 3 adjacent carbon atoms, whereas in diamond each carbon is bonded to 4 adjacent carbons. At almost 120 degrees. Why? Because it's almost trigonoplanar. Not completely, but almost trigonoplanar. So the bond angle is not going to be, it's going to be less than 120, but it's going to be between 109 and 120 degree bond angle. But for diamond, specifically, exactly at 109.5 degrees. For C60, also the bond angle is between 109.5 and 120. For H levels, we can go beyond. We can give more differences to suggest that each carbon is bonded, but also each carbon that is sp2 hybridized is bonded to 3 adjacent carbons. Each carbon atom that is sp3 hybridized is bonded to 4 adjacent carbon in diamond. Is there anything else we can say? We can maybe say that electrons are delocalized partially across the carbons of C60, while in diamond there's no delocalization of electrons. But that's pretty much it. Diamond sublime at higher temperature definitely than C60. Why? Because it's a giant covalent macromolecule. Diamond sublimes at higher temperature than C60 because of its giant covalent macromolecular nature compared to how C60 is not a simple covalent molecule, but it's quite complex, but it's a molecule that have intermolecular forces to compared to how C60 molecules have intermolecular forces, primarily London dispersion forces, LDF. State two features showing that propane and butane are members of the same homologous series. Members of the same homologous series have the same functional group and therefore the same general formula. And also because they differ by repeating units of CH2, they will have a general formula. They will have similar chemical properties and similar physical properties as well, but gradually differing physical properties with increasing carbon numbers. So we want to say that members would have the same general formula of what? What's the general formula of alkanes? CnH2n plus 2 would be the general formula, as well as members differing by repeating units of CH2. Similar chemical properties. They undergo similar reaction mechanisms like free radical substitution reaction. We'll skip this question as we have the mass spectrum data removed for copyright reasons. Presence of carbon to carbon double bonds, in other words alkenes, undergo the characteristic electrophilic addition reaction with halogens and other electrophiles. So therefore, bromine water testing could help us identify, could indicate the presence of carbon double carbon bonds. So if there is, we would have bromine water with the orange-brown color decolorizing. Why? Because as the halogen is, the bromine halogen, as it is electrophilically added to our carbon-to-carbon double bond, we're losing halogen identity. Halogen are integrated into our new halogenoalkane molecule. Therefore, double bond is lost, but the halogen is also lost. So the characteristic orange-brown color is lost as well. Butene is drawn, can be drawn as follow. Obviously, we can also draw butene as follow as well. For the HO purpose, we want to acknowledge how there's the Z annotation given at the beginning of butene, which is asking us to draw, to pick out the structural isomer with the two methyl substituent groups to be on the same side. So we want the first structural formula that we have drawn. But for the SL level, we don't need to know what Z stands for. Therefore, both drawings could work. But2-ene can be represented in condensed structural formula as CH3, CH, CH3, where there would be the double bond between the second and the third carbon, plus hydrogen bromide, which would lead to the hydrogen bromide being integrated into our but2-ene to become CH2, CH, Br, CH3. And we refer to this reaction as electrophilic addition. Easy question. Too easy. Actually, I'm going to regret that. I'm going to regret what I've just said about being too easy. We are having to compare NMR spectrum of but2-ene and bromobutane without the spectrum given. Okay, this is quite difficult. So let's draw out the hydrogen environments of but2-ene and 2-bromobutane. Let's go with but2-ene. What are the hydrogen environments here? We've got, firstly, symmetrical molecule, which means that we've got 6 hydrogens that occupy the same hydrogen environment. We've got 2 hydrogens that occupy another hydrogen environment. Now this will compare with 2-bromobutane, our product, where firstly there are more hydrogens, and we've got more distinct hydrogen environments as well. First hydrogen environment would be closest to the bromine. Second hydrogen environment would be the CH3 that is bonded to CHBr. Now there's the third hydrogen environment that is bonded to CHBr as well as CH3. The CH2 hydrogen environment is bonded to the CHBr environment on the right, and at the same time CH3 environment on the left, which is the final hydrogen environment. There are 4 different hydrogen environments in our 2-bromobutane. Okay, so how do we answer this? But2-ene will compare and contrast with 2-bromobutane. Firstly, with number of peaks, 2 versus 4. There will be further discrepancies of ratio of hydrogen atoms or peak intensities. We will have 6:2 ratio. We'll have 6:2 ratio for our but2-ene. However, for our 2-bromobutane, we will have 3:2:1 and 3 ratio. 3:2:1:3. Now that's all we need to know for SL level. But for higher level, we can go further to contrast the 2 spectrum. We could talk about chemical shifts. What is the characteristic hydrogen environment of butene? Well, I do see a double bond. Therefore, the double bond is going to be our characteristic hydrogen environment, and that is illustrated by 4.5 to 6.0 ppm chemical shift. What about 2-bromobutane? Well, we have a halogen right there. Therefore, the hydrogen that is bonded to halogen bonded carbon right here, 3.5 to 4.5 will be our characteristic. (3.5 to 4.5 ppm will be our characteristic hydrogen environment. There will be a peak at the two characteristic hydrogen environments for the two molecules. Now, the final contrast point, splitting patterns. We can also compare and contrast the splitting patterns for the two. Again, butene is quite straightforward. We have the CH3 bonded to the adjacent carbon with one hydrogen attached. And what does that tell us? It tells us that the CH3 will be a doublet. The CH3 will have a doublet peak, while the CH hydrogen environment will have a quartet. The CH hydrogen is adjacent to a carbon with 3 hydrogens, and therefore 3 plus 1 a quartet. Let's move to the final hurdle, 2-bromobutane splitting patterns. Starting off with CH3 in red. CH3 in red is bonded to CH2. 2 plus 1, a triplet. Difficult, very difficult. CH2 is bonded to CH3 on the left. Now that's 3 hydrogens. But not only is it bonded to CH3, but it's also bonded to CHBr. Now, it's bonded to 2 carbons that in total are bonded to 4 hydrogens. That's 4 plus 1. I think it's quintet. If we use the Roman numeral, it should be quintet, but let's just call it multiplet. Next up, hydrogen. The single hydrogen, again, is bonded to CH2 on the left, CH3 on the right. In total, 5 hydrogens, 6, 5 plus 6. Latin numeral is sextet, but again, let's call it multiplet. Finally, CH3 in orange is bonded to a CHBr. The adjacent carbon has only 1 hydrogen attached, which means that we will end up with a doublet splitting. Okay. We've gone through way too much info for a 2 marker. Go with the easy 2. Save yourself some time. The major product of reaction between but-1-ene and steam has a major change into the reaction mechanism. And what's that? We are reacting an unsymmetrical electrophile with unsymmetrical alkene. Therefore, we will have to apply Markovnikov's rule, where there will be 2 products formed, one of which will be major while the other is minor, and that's all to do with the stability of carbocation intermediate. But-1-ene will form a secondary carbocation intermediate as well as a primary carbocation intermediate. Now, which one's more stable? Which one do you think is more stable? Well, I'm going to vote for the secondary, not the primary. And why is that? It's because the central carbon atom with the positive charge is bonded to more alkyl groups. Who are the alkyl groups? It's going to be the methyl on the right and the ethyl on the left. And what do? They exert positive inductive effect, which help to minimize, to reduce that positive charge on the central carbon, and therefore increase the stability of our carbocation. And this will compare with the presence of only one alkyl group, and that's propyl, exerting, smaller positive inductive effect. So we would expect the major product to be the hydroxyl that will bond to the secondary carbocation intermediate, which will be buta-2O. That's the major, which means the minor would be buta-1O. The reason being is secondary carbocation intermediate is more stable. We're going through bromopropane, 1 bromopropane with sodium hydroxide, nucleophilic substitution reaction, specifically bimolecular nucleophilic substitution, SN2. The mechanism, when we draw them, needs to make sure we have curly arrows. From where to where? From our hydroxyl nucleophile, make sure there's the negative charge, originating curly arrow. To where? To the partially positive central carbon of halogen alkane. The halogen alkane being 1 bromopropane, we need to draw 1 bromopropane as such. Let's make sure we have drawn 1 bromopropane correctly. And I like using wedge and dotted drawing to make sure it's a 3D, to illustrate 3D mechanism. And we want to also show how the carbon to halogen, the carbon to leaving group, carbon to bromine single covalent bond starts to break. So that from the middle of the carbon to bromine single covalent bond, there's the originating curly arrow landing on bromine atom. This will lead to the formation of our transition state, where the transition state will have a planar, the hydrocarbon backbone. Now that's the planar hydrocarbon backbone that is partially bonded to the leaving group and partially bonded to the incoming nucleophile. Overall, negatively charged because of the negatively charged nucleophile. We still have 4 single covalents, it's just that the CBr and COH bonds, they count as 1 single covalent. They're partial single covalent bonds. Now, once the breakage of CBr bond is complete. Once the formation of COH bond is complete, we will have our final alcohol product. That looks like this. Please note how we have an inversion of configuration, as well as the bromide ion that has left. And it will probably bond with the spectator ion, sodium plus, around it. Again, splitting pattern of 1-bromopropane. Let's draw 1-bromopropane out first. C, 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 Br, 2 H's, 2 H's, 3 H's. We have 2 hydrogen environments. We have 2 hydrogen in the first hydrogen environment. We have the next set of 2 hydrogens in another hydrogen environment, and the final set of 3 hydrogens in the final hydrogen environment. There would be 3 peaks in 3 to 2 to 2 ratio, where the 3 hydrogens CH3 are bonded to a CH2, therefore will be in triplet. I'm going to skip the middle CH2 because it's the most difficult one and start with CH2. CH2 is bonded to another CH2, therefore 2 hydrogens plus 1, 3, meaning we have a triplet as well. The complicated middle CH2 is bonded to CH3 on the left and CH2 on the right. In total, 5 hydrogens are bonded to the adjacent carbon atoms. 5 plus 1, 6. That's a multiplet. Multiplet, or use the Roman numeral sextet. What reaction is this? Methane is reacting with chlorine to become chloromethane. That's free radical substitution reaction. We need UV light to supply the energy to initially create the chlorine-free radical. And we're going to look at the energetics of this reaction. Section 11 tells us that we will be using bond enthalpy values, where we will be breaking 4 CH bonds, 1 Cl to Cl, and we'll be forming 3 CH and 1 CCl, and finally 1 HCl. Enthalpy change, delta H, is going to equal to sum of the bond enthalpies of our reactants. Why? Because we need to input the energy that corresponds to the bond enthalpy values of our reactants to break them. And we represent this as what? Sum of bonds broken. We'll be subtracting sum of the bonds formed. Why? Because the new bonds formed will be releasing energy, and that will take negative sign. Let's go to our section 11 to look at bond enthalpy values, starting off with CH having 414, ClCl having 242. So 414 times 4 plus 242, nice numbers, take away 414 times 3 plus CCl. What is the bond enthalpy for CCl? 324. 324. And we need to take away again HCl. What is HCl? HCl. Sorry, that's not HCl. HCl is 431. 431. Let's just make sure that we have counted correctly. In methane, there are 4 CHs. In Cl2, there's 1 Cl to Cl. In CH3Cl, there are 3 CH, 1 C to Cl, HCl, H to Cl. We have not left out anything. If we do the math correctly, we'll end up with a kilojoules per, we'll end up with kilojoules value, which would be minus 99 kilojoules. And we can draw an energy profile diagram for our free radical substitution reaction, where we know, being an exothermic reaction, we will have, let's draw the enthalpy of reactants at a higher value, being an exothermic one. We will have the reactants, that's what? Methane and chlorine. And we will have also the products, which is what? Chloromethane and hydrogen chloride. We will have delta H value. That corresponds to the value we have calculated as minus 99 kilojoules. Not displayed, but we can also speculate how that will be. The transition state as well as the activation energy. That was it. That was paper 2 from May 22, Timezone 2. Relatively easy compared to previous year or Timezone 1. But there are some difficult questions, especially regarding the NMR spectrum analysis. And hopefully it was useful. And yeah, best of luck with your IB Chem studies.